The Earth is 4.5 billion years old. That's 4,500 million years, or 45 followed by 8 zeros. Over that vast amount of time, our planet didn't always look like it does today, with lots of plants and animals, big oceans of liquid water, and breathable oxygen in the atmosphere. If you had to guess, what do you think the first 100 million years of the Earth looked like?
Ooh, that's a good question. I want to say boiling oceans of magma.
Yeah, I think that sounds right. And I feel like there were also asteroids and lots of meteorites hitting the planet. And with the way you phrased the question, I'm guessing it wasn't just liquid water or an atmosphere like we have today.
So are we right?
Well, I don't actually know, because this is something geologists are still arguing about. How did the early Earth over 4 billion years ago evolve into the planet we know and love today? It's a big question and an open question. To get answers, geologists turn to a surprising source, a tiny mineral no bigger than the diameter of a human hair that has secrets about our planet locked away inside its crystal structure. This minuscule mineral with its big stories is called zircon.
Welcome to Tiny Matters, a science podcast about the little things that have a big impact on our society, past and present. I'm Sam Jones, and today I'm joined by my co-host, Deboki Chakravarti, of course, and also Rudy Molinek, a geologist and science journalist who hosts the podcast Under Our Feet. I don't know if we've ever brought a third co-host for a special episode.
Yeah, I don't think so, but welcome, Rudy.
Yeah, welcome.
Thanks for having me. I'm really glad to be here.
Our show today is about that tiny mineral zircon that Rudy just mentioned, and the big secrets it holds about the earliest history of our planet and even the solar system and beyond. We'll talk about what zircons are and how they answer that question we started with, what the conditions on the early Earth were like. We'll also hear about some of the big discoveries made from zircons and find out what scientists are looking for next with these miniature crystals.
I first got interested in zircon minerals about 10 years ago in the summer of 2014. I was a little undergrad geologist, and I got to go up to Alaska for a month of geologic fieldwork. The trip was awesome. It was a really warm summer in Alaska, and we spent our days zipping around Prince William Sound in 2 inflatable Zodiac boats. We saw orcas jumping around, otters floating and playing in the bays, grizzly bears popping up from the tall grass on shore, even porpoises chasing and playing near our boat. We ended every workday around mid-afternoon to fish for halibut for our dinner.
I consider myself an indoor person, but that sounds like an amazing day.
Yeah, it's pretty ideal, honestly.
I agree, but I'm a geologist, and I once had a professor tell me to ignore, quote, everything that's alive, so I could focus on the rocks. In between all those wildlife sightings, we were collecting dozens of 20-pound chunks of sandstone, which we shipped back to the lab in Minnesota to crush and grind all into dust, just so we could separate out a few tiny ancient grains of zircon. Ever since that summer, I've had zircon stuck in the back of my mind. I always found it so cool that these teeny tiny little minerals with a kind of science fiction sounding name could tell such big stories. And now I get to learn more about them and share that with you and your listeners. One thing I've observed over the last 10 years since that trip is that geologists talk about zircons all the time, but my non-geologist friends have never heard of them.
Yep, that would be accurate for me.
Yeah, that's true for me. I am the non-geologist friend who has never heard of a zircon before.
And I'm guessing that's true for a lot of the Tiny Matters audience too. But that doesn't mean you haven't met a zircon.
So zircon's actually quite a common mineral in that we find it in many, many different types of rocks. It's almost always a trace mineral, present as less than 1%. So if you don't look for it, you might not even know it's there. But it's hard to walk on dirt anywhere without having zircons beneath your feet.
That's John Valley, a professor emeritus of geoscience at the University of Wisconsin-Madison, who specializes in geochemistry, a field of science that applies the tools of chemistry to things like rocks and minerals to understand the processes that shape the world around us.
I pretty much study anything that has to do with Earth history. and a little bit to do with Mars and the moon. But one of the things I'm really passionate about is the earliest history of the Earth, where we don't have very much evidence, and therefore it's challenging and very interesting to study.
John has worked with zircons for decades and is a leading expert on using the minerals to understand the early Earth.
So, what exactly are zircons? And what makes them so useful to geologists like John? At the most basic level, zircons are the chemical compound zirconium silicate. They have a crystal structure that's made up of a zirconium atom connected to a silicon and 4 oxygen atoms. Silicate minerals are very common. They're the most abundant minerals in the Earth's crust. For example, quartz is a really common silicate mineral. But the element zirconium is pretty rare, which is why, as John told us, zircon minerals make up less than 1% of many rocks on the surface of the Earth. Usually with rare minerals, people get most excited about the big ones, the gems that go into jewels and are on display at museums. That's true for zircons too, but geochemists like John look at them a little differently.
It can be very pretty. There are people who mount zircons in rings. It's gorgeous. It's a birthstone. But the zircons that geochemists get excited about aren't the big gemmy ones.
The big gem-quality pieces of zircon you might see in jewelry have to form in very specific environments that aren't as informative for geologists who are studying the early history of the Earth. And also, because the big ones are so rare, they're probably too precious to cut up for geologic analysis. So the zircons geochemists like John look for are only about 1/10 of a millimeter. That's about the diameter of a human hair.
And these zircons are really, really durable. For example, many zircons form in granite, an igneous rock that solidifies slowly as melted magma cools beneath the Earth's surface. When that granite later gets exposed to rainwater, which is slightly acidic, other minerals called feldspars start to break down and the rock falls apart. But the more resistant minerals like quartz and zircon are left behind.
That's why beach sand is usually mostly quartz. That sand is the remnant of a solid rock that's been broken down, and only the most hardy mineral grains make it through that process.
Exactly, but John told us if you pick up a handful of beach sand, there's a good chance there are zircons in there too, even if you can't see them. But the journey of a zircon doesn't necessarily end at a nice sandy beach. If, say, that beach gets buried and turns into sandstone over millions of years, the zircons still survive. And if that sandstone gets buried deeper and deeper into the earth to the point that extreme heat and pressure turns it into a different type of rock entirely, the zircon pieces will still stay whole.
So zircons can last through pretty much anything Earth throws at them and still be around even billions of years later when geologists like John go looking for them.
So once zircons form, they're pretty much forever. I think they're more important than diamonds, and so I like to say zircons are forever.
I think I see a new marketing campaign. Just kidding. I'm not trying to sully the reputation of zircons.
Zircons have another important property too. We said earlier that their crystals are made up of atoms of zirconium, silicon, and oxygen. And that's true for the most part. But the zircons can also fit in a few uranium atoms here and there when their crystals form.
When I think of uranium, the first thing that I think of, and that most people I think of, is radioactivity.
That's exactly right, and that's really important to the science of zircons. Uranium, which scientists call a parent isotope, radioactively decays to lead by ejecting protons and neutrons from the atom's nucleus. Once it gets to be lead, the atom is stable and not radioactive anymore. But importantly, lead doesn't fit into the zircon's crystal structure when it first forms. So any lead contained in a zircon crystal would have to have come from that initial uranium breaking down. Scientists know how long this radioactive decay takes, so by comparing the amount of uranium to the amount of lead in a zircon crystal, they can figure out exactly how old it is.
So the reason that zircons are interesting for geologists and planetary scientists is because they are our timekeepers.
That's Carolyn Crow, a planetary scientist at the University of Colorado Boulder, who studies the Earth, Moon, and other planets by looking at samples of lunar rocks or meteorites.
The great thing about zircons is the zircon crystal structure will take in a bunch of uranium, so we'll take in a bunch of this parent, and does not want to take in lead. Lead does not fit in this crystal structure. And so what that means is that you get a very clean start to your clock. And so you can get very nice ages of samples for when they form.
Carolyn told us that this method of dating zircons with uranium is similar to using a little math to figure out how long it might take to drive somewhere.
Say I'm here in Boulder and I want to drive to Denver, and I know that it's 30 miles away or something like that. And I am going to drive at a rate of 60 miles per hour. I can do a calculation and say it's going to take me 30 minutes to get there, right? Half an hour to get there.
For radioactive decay, knowing the amount of uranium and lead is kind of like knowing the distance you need to drive. And knowing the rate of decay is like knowing the speed of your car.
How long does it take me to get to Denver? Well, how long does it take for uranium, the amount of uranium that you've measured to decay into the amount of lead that you've measured? So if we know the rates very well, then we can figure out the ages with really good precision.
So geologists use zircons to figure out the age of all sorts of events in Earth's history. And the fact that the mineral is so durable means it's a really good timekeeper for the geologic past. But let's take that to the extreme. Given that zircons pretty much last forever and they're really good at telling us how old they are, a natural thing to look for is the oldest possible zircon, as close to the formation of the Earth as possible. For scientists who study that time period, really old zircons are exciting because they could hold clues to some unsolved mysteries about what the earliest years of the planet were like, answering questions like, when and how did water get onto our planet? When did the surface of the Earth become habitable to life? And how long after that did life first emerge?
And one of the reasons we were really excited to talk to John, who you heard from a few minutes ago, is that he's part of the team that found the oldest zircon ever. In fact, that tiny zircon is the oldest piece of the Earth that's ever been found. And it had a big story to tell. We'll get to that in a minute, though. First, let's set the scene. To find really old zircons, geologists start by looking for really old rocks. John found his more than halfway across the world from his home in Madison, Wisconsin, in a remote part of Australia called the Jack Hills.
As a child, I was taught that if you drill a hole underneath where you live, you'll come up in China, but that's not actually true because China and the United States are both in the northern hemisphere. And so if I drilled a hole under Madison and I went right through the center of the Earth, I'd come up in the Indian Ocean about 1,000 kilometers from Perth, Australia. And so in order to get to the Jack Hills, we fly to Perth, Australia, which requires quite a few flights from Madison. And then we drive about 700 miles north. And the first 500 miles are paved, and then it's 200 miles on dirt roads.
The Jack Hills, amidst the red rocks and vast sheep ranches of Western Australia, are a distant and desolate place. John and his colleagues would camp near the house of the folks that owned the land, since it was the closest source of good drinking water to the rocks they were studying. But even that camp was still 50 miles from the rock outcrops they were looking at.
Yeah, you'll see some kangaroos and some emus and eagles and not much else. And there's for sure no water. And so what are the hazards? Usually when you do geological field work, you're worried about falling off a cliff or getting bitten by a snake. And yeah, those things could happen. But the biggest hazard in the Jack Hills are flat tires. And if you have more flat tires than you have spares, and you're 50 miles from the nearest place, then that's a long, dry, thirsty walk out.
The rocks there are metamorphosed conglomerate and sandstone quartzite. That's a mouthful, but it just means the rocks used to be a pebbly and sandy sedimentary rock with a lot of the mineral quartz. But they've since been cooked deep in the earth. They're over 3 billion years old, from a time period called the Archean Eon. If we substitute distance for time, and the modern day was at one end of a 100-yard football field, and the formation of Earth was at the other end, with all of Earth's history stretched out in between, these rocks would have formed about 70 yards away from where we're standing now. For some context, the asteroid that caused the extinction of the dinosaurs struck Earth about 65 million years ago. That's only 1.5 yards away from where we're standing.
And the zircons in this rock are even older. Since it was a sedimentary rock before it metamorphosed, that means it's originally made up of bits and pieces of older rocks that broke down to deposit their most durable mineral grains, like our zircons, as a sediment. So any zircons in the Jack Hills had to have formed in a molten magma well before the rock was deposited so they could erode and make their way into the sand.
A few years before John got involved, other researchers had found zircons in the Jack Hills that were around 4.2 billion years old. The Earth itself is 4.5 billion years old, so we're getting pretty close there. John knew it could be a fruitful place to search for old zircons that might tell him something new about the earliest years of the Earth. He contacted a geologist in Australia named Simon Wild, who had some zircons from the Jack Hills that he hadn't figured out the age of yet. Wild told John that he'd analyze the amount of uranium and lead in the crystals and get back in touch. From there, it took some time before John heard anything.
2 years later, I got this excited email from Simon saying, well, I've just run a handful of zircons, and I didn't find one that's 4.2, but I found one that's 4.1, and I've got another couple days on the instrument next month, and I'll let you know how it turns out.
Even a 4.1 billion year old zircon would be exciting for John. His plan was to take old zircons and analyze the oxygen atoms in their crystal structure. That's because oxygen has a few different isotopes, meaning they're still oxygen, but they just have a different number of neutrons. One of the isotopes, a rare form called oxygen-18, is heavier than the most common form, oxygen-16. All zircons that form directly out of the Earth's mantle have the same ratio, which matches the relative abundance of the isotopes. But if the zircon is forming at a cooler temperature compared to the mantle, it will take on more of the heavier isotope. John was looking for the oldest oxygen he could find in the oldest zircons on the planet to see what the temperature on Earth was like back then. If the ratio of oxygen isotopes matched that of the Earth's hot mantle, it would mean the dominant scientific thinking of the time was correct, and that the first few 100 million years of Earth history were hot and the planet was covered in magma oceans, with perhaps just a thin, solid crust forming in places. Any zircons that formed would have crystallized directly out of that molten magma. In the meantime, Simon Wild kept on dating zircons.
A month later, I got this very excited email from Simon. I can't believe it. One of the zircons I just dated is 4.4 billion years old. And so it was way older than anything that had ever been dated, and it was really older than anything we'd even imagined might exist.
John told us that geologists call the first 500 million years of Earth's history the Hadean. Hadean as in hell.
And it was thought to be so hot, and there were magma oceans on the surface of the Earth, that nothing would have survived. And so nobody thought there would be samples of the early Hadean Earth preserved.
But apparently, some Hadean samples in the form of zircons could survive. He and the team headed to Edinburgh, Scotland, where a very specialized instrument could make precise oxygen measurements.
So we just ran tests for like 12 days, running other things and standards until we really thought the machine's working well. Let's put in these precious zircons and see what happens. And so I did that on the night of the 12th day. And sometime in the middle of the early morning, I got these oxygen isotope ratios back. And I knew exactly what they're going to be, all right, because I'm a professor and I'm supposed to know these things. And it was going to be just like the zircons that come from the mantle. But the numbers I got were a little higher.
The amount of oxygen-18 was so much more than what John expected from zircons that formed in the Earth's mantle that it didn't seem there was any way it could be some error in the measurement or instrument. But they still spent 2 days running tests and making sure they had everything airtight. When they were satisfied, they had to figure out why the oxygen isotope ratio was so high.
For clues, they thought about younger rocks, where zircons with high oxygen isotope ratios are common. If a rock sits at the surface of the Earth for a while today, it eventually interacts with liquid water. That interaction brings in different oxygen, leading to more of the heavier isotopes. If that rock is then buried deep into the planet and remelted, it retains that heavy oxygen. This happens all the time today, but since scientists at the time assumed that in the Hadean Eon, the world was super hot and magma was right near the surface, it didn't seem like those ancient rocks would have liquid water to interact with. But once John and his team let go of those assumptions, it began to feel like there had to have been liquid water that early in Earth's history.
The only thing that was unusual about these zircons from the Jack Hills was their age. The oxygen isotope ratio is really perfectly explainable once you get over a number of things that you're supposed to know, one of which is that there were magma oceans when this happened. Well, that apparently is not the case. The other is that there's no crust when this happened, which is not the case. And the other is that the surface of the Earth was really hot and Hadean. And what this was saying is that the surface of the Earth was cool enough that liquid water would have been precipitated to form oceans. And this was telling us that there were oceans and relatively clement conditions on the surface of the Earth going all the way back to 4.3, maybe even 4.4 billion years ago.
That's way earlier than scientists previously thought, and they published their results in the journal Nature in 2001, which was a massive jump forward in the study of the early Earth.
I think it's pretty incredible that from this one tiny crystal of zircon that's only the size of the diameter of a human hair, these scientists were able to make such a big discovery about the entire history of Earth. We went from thinking our planet started out with 500 million years of boiling magma oceans to realizing there was likely liquid water and relatively cool temperatures on the surface within 100 million years after its formation.
I agree. And there are a bunch of other stories like this we could tell about how information from zircons has changed our whole understanding of Earth, like when the process of plate tectonics might have started, when the atmosphere became heavily oxygenated, when the first life emerged, how continents have moved around over time. But I think that might be keeping the zircon story too small.
Really? That all sounds quite big to me. We're talking about a microscopic piece of rock that's over 4 billion years old and could tell us about the conditions under which life evolved.
Yeah, that's true, but we're still just talking about only one planet. It turns out scientists have found zircons in rocks astronauts brought back from the moon and in meteorites from all over, including Mars, and are using them to learn about the solar system and beyond. Before we get into that, though, let's address a big question. With everything happening here on Earth, why should we care about other celestial bodies?
This is a great question. Like, why are we interested in studying moon rocks and Mars rocks and things that aren't from here? Let's start with our Earth-centric focus. We want to know about Earth, the processes that happen on Earth. How did Earth form? How did it evolve over time? Okay. Well, on Earth, we have lots of different processes like plate tectonics, volcanism, erosion that are constantly resurfacing the Earth.
That's Carolyn Crowe again, the planetary scientist you heard from earlier. What she means is that because of all the active processes on Earth, rocks are constantly getting torn up, remelted, or buried by new rocks. And that makes it really hard for old rocks to stick around long enough for a geologist to find and study.
Right, and think about the story John told about the Jack Hills. Even though that zircon was 4.4 billion years old, the rock they found it in was a sedimentary rock that was much younger. So there's not much full rock evidence of the early Earth.
So if you want to know what's happening 3.5, 4 billion years ago, during an interesting time in Earth's history when we have oceans forming, we have an atmosphere forming, we have life emerging, we really do not have a good rock record. We don't have many rocks from that time.
But the moon separated from the Earth just after the planet formed, when an object the size of Mars slammed into the young Earth and spun off a big chunk that became our moon. And now the moon doesn't have most of those processes that Carolyn mentioned, like plate tectonics and erosion, that get rid of old rocks. So there's a lot of evidence in lunar rocks that's been preserved much better than it has on Earth. That means that if we want to understand the early days of the Earth, looking at the moon is a good idea.
The moon has been basically the witness plate of our solar system environment during these times in Earth where we are going through big changes. Life is emerging, right? We have mass extinction events more recently due to impact craters, and we can learn about these important milestones in Earth's history by looking elsewhere.
So that's one of the reasons for looking at the moon. It can tell us about a part of Earth's history that's been essentially lost here at home. But it doesn't stop there, and that's part of why Carolyn studies meteorites from places further away too.
For looking elsewhere, looking at Mars, looking at other planets, we can expand our Earth-centric view out and say, well, we can understand what our local environment, what's going on dynamically what's hitting us, what's being delivered. But then if we want to know from a solar system-wide perspective, how do all the planets form? Why are the planets different? We have to look at these rocks, these traces that we have to answer some of those questions.
For her work with lunar samples, Carolyn mostly does research on rocks from the moon that were brought back from the Apollo missions in the 1960s and 70s.
I just want to say that it's so cool that even 50 years after the Apollo missions stopped sending astronauts to the moon, scientists are still using the rocks they brought back to make new discoveries.
Yeah, it's really, really cool. And it turns out NASA is planning to send astronauts back to the moon again as early as next year as part of the Artemis missions. Given how much science has been done based on the original Apollo missions, that's a really exciting prospect for scientists.
But back to Carolyn's story. Even though the geologic processes on the moon are simpler than here on Earth, it doesn't necessarily mean the rocks she studies are basic too.
These samples are not simple Earth rocks. They've been through many different impact cratering events. So if you go out and look at your concrete sidewalk and there's a chip taken away from the concrete, you'll see all these little rocks within the cement. And that's kind of what moon rocks look like. They're called breccias, but they have this same structure where you have all these little individual rocks that are kind of fused together and cemented together through the impact process.
So a single lunar rock can have a history of multiple impact events. To untangle that story, Carolyn turns to our old friend, the zircon. The first thing she looks for, like John, is how old the zircon is, to know during what part of Earth-Moon history it formed. Then, to learn more about the impact history the zircon has experienced, she looks at them really, really closely.
They survive through lots of different things. That's why they're forever. You can throw them into another magma and they can survive. You can shock them to tens of GPa and flash heat them in an impact structure and they still survive. And when they are surviving, they're not just surviving in a pristine way. They can be altered. And they have all these different alteration textures that can tell you about the conditions that these zircons have experienced.
In the lab, Carolyn can untangle the history of a zircon on the moon or beyond, and in doing so, learn more about the history of our planet and our solar system. And every single time, she finds something new and exciting.
When you're working with planetary samples and you're working with impact craters, pretty much everything that we look at is surprising because it's so complex. And even though impact cratering is one of the main geologic processes and the dominant geologic process in the solar system, we really don't know that much about it.
The same is true of the early Earth. So to wrap up our zircon story today, I want to stick with this theme of zircons being a rich source of information about parts of our own history that we still just don't know that much about, but that geologists have spent decades focused on. I mean, details surrounding when life first emerged on Earth are still pretty fuzzy.
Well, there's so much we don't know about the early Earth. The oldest microfossils are 3.5 billion years old, the oldest that anybody can agree on. There are lots of things that are older, but they're not as convincing. And yet we have evidence that there were habitable oceans 800 million years before that. So we'd love to know when the first evidence for life emerged. We'd like to know more about the first billion years of Earth's history, and especially the first 500 million years.
Luckily for us, and for scientists who study the early Earth and solar system, we have the perfect mineral to study such big questions about the deep past: zircon.
It's very resistant to change. It's a hard mineral, it's chemically resistant, it's thermally resistant. Zircons pretty much last forever in the rock record. And so if I was De Beers, I'd be advertising zircons are forever.
All right, Rudy, welcome to your first tiny show and tell. We're going to do a real short one today because
we got to spend so much time learning about zircons.
We got to spend so much time learning about zircons that we have to do a quick tiny show and tell.
In some ways, you did the tiny show and tell. This was like a big show and tell.
It's true. It really is. My tiny show and tell is some cool gladiator news.
Oh.
So there's this belief that gladiators fought animals in the arena, which of course we've seen popularized through films like Gladiator. But there's actually been really little physical proof that that happened. And now researchers have identified bite marks from a large cat, they think a lion, on the pelvis of a gladiator skeleton that would have ultimately been fatal. Sounds painful. And I guess he was also decapitated, which they think might have been a mercy kill after he was bitten. But yeah, evidence that like maybe some of what we're seeing in Gladiator is not fully made up. But there's a lot that probably is super made up.
I'm glad we have the science behind Gladiator.
Yeah, very, very important.
And also, oh my God. Ugh.
Yeah.
Well, Sam, I guess mine is also kind of related because it's about fighting.
Okay.
There's a little bit of territorial stuff. I'm talking about the warty birch caterpillar, though, not gladiators. Warty birch caterpillars, they're small, they're vulnerable, and they spend their early days living on like the little tips of the little birch leaf that they're on, that they just like stay up there on the tip. But obviously other caterpillars want that space too, so they've got to fight them off. And how do they do this? They vibrate threateningly at them. They hit the leaf, they scrape their body on the leaf, and they do that to try to like say like, no, this is my little corner of this leaf. But if they can't do that, like if that doesn't work, they see their rival and they're like, nah, this is not for me. They will make a quick getaway by releasing a silk thread that they can just like ride down.
Wow. I love that.
Yeah.
Good for them.
Good for them. Yeah.
Rudy, do you want to share something?
I think I'll let y'all keep yours because it had the nice thematic pairing there. So I'll just let y'all do your two, and that'll be good.
That sounds good.
Thanks for tuning in to this week's episode of Tiny Matters, a podcast brought to you by the American Chemical Society and produced by Multitude. This week's script was written by Rudy Molinek and edited by me, by Michael David, and by Sam Jones, who is also our exec producer. It was fact-checked by Michelle Boucher. Our audio editor was Jeremy Barr. The Tiny Matters theme and episode sound design is by Michael Simonelli and the Charts and Leisure team.
Thanks so much to John Valley, Carolyn Crow, and our guest co-host, Rudy Molinek, for joining us. Go rate and review us wherever you listen. We super duper appreciate it. And we'll see you next time.